Hello guys, welcome on Tesla Adventures. Today in this video, I have compiled level 1 numericals of solids and elasticity. And in this first question, it is given that there is a brass rod of diameter 4 mm. I always recommend that you should always underline the data in the question while doing the question paper. So it would be very easy to find out that data quickly and to use it in solving the numerical. So you should always underline and you should always write down the data separately. So D is equal to 4 mm and this is 4 into 10 raised to power minus 3. The Young's modulus of brass is 9 into 10 raised to power 10. And the strain developed in percentage is given as 0.1%, which means that delta L by L into 100 is 0.1%. So delta L by L is equal to 0.1 into 10 raised to power minus 2. Okay, now we know that force upon area is equal to strain into Young's modulus. This force upon area is stress. So force we need to calculate and area is pi d square by 4. And strain is 10 to the power minus 3. You can see that this is 10 to the power minus 3. And gamma is 9 into 10 raised to power 10. So F is equal to pi d square is 16 and this is 10 to the power minus 6 and divided by 4 into 9 into 10 raised to power 7. So this is 36 pi into 10 raised to power 1. So F is equal to 360 pi. So this force is required to stretch this wire by 0.1%. Now we move on the next question. In this question, there are two wires of same material and same length, but their diameters are in ratio of 1:2. These wires are stretched by the same force, and we have to find out the ratio of their elastic potential energies per unit volume. So let us denote the elastic potential energy per unit volume by small u, and its formula is half stress into strain. We know this formula very well. So we can say that strain in both of these wires will be different because their area is different. So we can say that let us denote that stress is equal to sigma. Now as strain is different, we can just do one thing, that we can write strain as stress upon Young's modulus. We can write down this strain as stress upon Young's modulus, and therefore energy density formula becomes half stress square upon Young's modulus. So this is the formula for energy density. Now we know that stress is equal to force upon area and area is pi d square. So we can see that stress is inversely proportional to square of diameter, and therefore u1 by u2 will be the ratio of energy densities of the two wires, and therefore it would be the ratio of stress developed of two wires and its square. So we already know that energy density is proportional to the square of stress, and stress is inversely proportional to the square of diameter. So we can conclude that this energy density is proportional to the fourth power of diameter, and it is inversely proportional to the fourth power of the diameter. So u1 by u2 will be equal to d2 to the power 4 upon d1 to the power 4. So u1 by u2 is equal to, so d to the power 4 is 2 to the power 4 upon 1 to the power 4, and it is equal to 16. So U1 by U2 will be equal to 16. So the correct answer will be option number 1. Now we move on the next question. In this question, it is given that steel has a breaking stress of 6 into 10 raised to power 6, which means that if this much force upon area will be applied on the steel, then it will break. Now we are suspending this steel wire with a roof, and we have to find out the maximum length of this steel wire which we can suspend from the roof so that it may not break due to its own weight. So the breaking stress is this, and it is equal to the mg of wire upon area. Now this mass upon area, and if we multiply both sides with length, then it becomes mgl by volume. A into L is volume, and mass per unit volume is given as density. So 6 into 10 raised to power 6 is equal to 8 into 10 raised to power 3 into G is 10 and into this length L. So L is equal to, this is 3 by 4 into 10 raised to power 2. You can see that. So L is equal to 0.75 into 10 raised to power 2. So L is 75 meters. So the correct answer is option number 3. Now we move on the next question. In this question, you can see that two wires are given, and the stress and strain curve for these two wires A and B is shown. So we have to answer the following questions. That first one is the fact that which of the material has greater Young's modulus. So we can see that stress upon strain is gamma, and therefore the slope of this graph, stress and strain, is gamma. So slope of A is greater than slope of V. You can see that this angle is bigger than this angle. So the slope of graph A is greater than the slope of graph B. So we can say the Young's modulus of A is greater than Young's modulus of B. The material which is more ductile, it means that the materials which has a greater plastic region. So this has the greater plastic region. So A is more ductile than B. The material which is more brittle, which means that it breaks just after the elastic point. So this, you can see that there is a shorter region of plastic region for B, and A has bigger plastic region. So the fracture point of A would be at this point and fracture point of B would be at this point. So the brittle material which breaks easily is B. And which material is more stronger? And it is obviously A, because more stronger material is that material which has more gamma. So the gamma of A is greater than gamma of B, as well as the fracture point of A is far away from fracture point of B. So we can say that the more stronger material is A. Now we move on the next question. In this question, there are two wires. This is A and B. Wire A has a radius of RA and wire B has a radius of RB. And there is a block of mass M which is connected between these two wires. A force of mg by 3 is applied on the lower end of the wire B. Then we have to choose the correct option. Now first of all, let us see that the stress developed in wire A will be equal to F. In fact, I am talking about wire B. So it is equal to F upon pi RB square, where F is mg by 3. So this is mg by 3 pi RB square. Now the stress developed in wire B, in fact A. Now A has a total force of F plus mg. So this will be F plus mg will be 4 by 3 mg, because F is mg by 3 and mg plus mg by 3 is 4 by 3 mg, and area is pi r a square. So these are the stress developed in these two wires. So if RA is equal to RB is equal to R, so stress in A will be equal to 4 by 3 mg upon pi r square, and stress in B will be equal to mg by 3 pi r square. So you can clearly see that stress in A is greater than stress in B. Okay, so wire A will break if RA is equal to RB. Now, if let us equate that if stress in A is equal to stress in B, this is another condition. So if we equate these two stress, then it would be 4 mg by 3 pi RA square is equal to mg by 3 pi RB square. Cancelling this 3 pi. Then we can see that 4 RB square is equal to RA square, and 2 RB is equal to RA. So this is the condition when the stress in both wires are equal. Now if 2 RB is greater than RA, which means that if we increase this term 2 RB here, if we increase, or we can say that RB is greater than RA by 2. So if we increase RB further, then you can see that if RB increases, then stress in wire B, this is wire B, it would decrease. So stress in wire B will decrease. And if we decrease RA, then stress in wire A will increase. So for same load, if wire A is thinner, then the probability that it would break would be higher. So B option is also correct. Now if RA and RB, if RA is equal to RB, then either of them can break because stress in both of them is equal. And the option D that says that length of A and B must be known to predict which wire will break, this is not correct, because the breaking stress is not dependent on the length. Therefore, the length information is not required. So the correct answers are A, B and C. Now we move on the next question. In this question, you can see that there is a load. Let's suppose it is W, and there are two wires which are of same material and same length, but in fact their Young's modulus is different, so material cannot be same and their length is same. So the cross section area of these two wires is also same. We have to find out the equivalent Young's modulus of these two wires. So we consider the spring analogy, and we consider them as a spring, that there are two springs which are connected to this load W, and the spring constant of each of this spring is K1 and K2. So K1 will be equal to gamma 1 A by L and K2 will be equal to gamma 2 A by L. Now in parallel, the equivalent spring constant K equivalent is equal to K1 plus K2, and equivalent spring constant will be gamma equivalent into area. Now we know that if we consider that A is the cross section of one of the wire, then for total both of the wires, the total cross section would be 2A. because with this load, a total of A and A 2A cross section is connected. The length will be same because both the wires have same length, and it would be gamma 1 A by L plus gamma 2 A by L. So gamma equivalent will be equal to gamma 1 plus gamma 2 by 2. So the correct option is option number B. Now let's move on the next question. In this question, there are 4 wires of same material and they are applied with the same force, same load. The dimensions of the wires are given below as set of 4 options. So we have to find out that which wire will have the maximum elongation. Now we know that F upon pi d square by 4, which is force upon area, which is stress, is equal to gamma into delta L by L. So delta L will be equal to F L by pi d square by 4 gamma. And you can also observe that delta L is proportional to L and inversely proportional to d square. Which means that out of these 4 options, the set of values of diameter and length, which has maximum value of d by L by d square, will have the maximum elongation. So you can check out the option number A, which says that L is equal to 1 and D is equal to 1 mm. So you can find out L square, L by D square. So this is 1 upon 1 square, which is 1. If you are imagining that why I have not converted the units, so you can easily understand that in all of these 4 options, the units are same. So I just need to compare these 4 options. So there is no unit conversion is required. So this 1 upon 1 square, which is 1, and this is 2 upon 2 square, which is 1 by 2. This is 0.5 upon 0.5 square. So 0.5 upon 0.5 square will be equal to 2. And this is 3 upon 3 square, which is 1 by 3. So the highest value of L by D square is for option number C. So the highest elongation would be in the wire which has the diameter of 0.5 mm and the length of 0.5 meters. Now we move on the next question. In this question, there is a wire of cross section area A, and this wire is clamped between 2 walls. The distance between the 2 walls is 2L, and if a load is applied on this wire at the midpoint, then its midpoint is depressed by a distance of x in the bottom direction. Now let us see that due to this weight W, it has depressed by a distance of x, and this length is L, this length is L. Now let us suppose that this length is L dash, new length. So L dash would be greater than L for obvious reasons, and L dash will be equal to under root of x square plus L square by Pythagoras theorem. So L dash will be equal to, if I take L common, then it would be equal to 1 plus x square by L square to the power half. And it is given in the question that x is very less than L. So we can apply binomial theorem, and therefore L dash is equal to L into 1 plus x square by 2L square. Okay, so now L dash is equal to L plus x square by 2L, and L dash minus L is equal to x square by 2L. Now strain produced in the wire will be change in length upon original length. Therefore, strain is equal to delta L by L. Now this delta L will be equal to L dash minus L, and this is x square by 2L square. So the correct answer would be option number C. Now let's move on the next question. Now in this question, there is a graph given. In fact, four graphs are given, and each of them is a graph for load versus elongation for four different wires of same material and same initial length. So we have to point out the thinnest wire among these. So we know that the force applied per unit area is equal to delta L by L into gamma and F is equal to A gamma by L into delta L. So this is Y and this is X, and therefore this graph is a straight line because Y is proportional to X. Now this represents slope, and the slope is equal to A gamma by L. So you can see that the area is directly proportional to the slope, area of cross section. And the thinnest wire would be that whose slope will be lowest and whose area will be lowest. So for the thinnest wire, area should be least, and for least area, slope should be least. So the least slope is of OA, you can see. So the correct answer will be option number C. Now we move on the next question. In this question, there is a metal wire of length L and area of cross section A, and its Young's modulus is gamma. This wire is stretched by a variable force F in such a way such that F is always slightly greater than the elastic force developed in the wire. So it means that this F is just enough to elongate the wire, and for calculation purposes we can take this F equal to the restoring force developed in the wire. Okay, so let us see that at any instant of time when the elongation in the wire is X, then the restoring force developed in the wire is Kx, where K is gamma A by L, where L is the total length of the wire, original length. Now, restoring force and the external applied force are equal because this external force is applied in such a way such that it is just equal to the restoring force. So we can take this external force as equal to Kx, and the work done in stretching this wire will be F into dx. If we stretch this wire by a small amount dx, then dw will be kx dx, integrating both the sign, then w will be equal to half k x square. Now x is elongation developed and the elongation, complete final elongation in the wire is L, so it is 0 to L. So work done in elongating this wire is half k L square. Now if we substitute the value of k, then it is gamma A by L, and this is L square. This work done is stored in this wire in form of the elastic potential energy, and therefore this complete work done is stored in the wire in form of elastic potential energy, and therefore this heat developed in the wire will be 0. So heat will not be produced in the wire, and the work done by this force will be gamma A L square by 2L, and the elastic potential energy stored in the wire is gamma A L square by 2L. Now in this case there is no heat developed in the wire, but if we apply a constant force, constant external force, then heat would be developed, and the heat developed in that case would be equal to the elastic potential energy stored in the wire. In this question, you can see that there is a graph between weight which is applied on a wire which is suspended from a roof, and the extension in the wire is plotted. So this graph looks like that. The length of the wire is 1 meter and the area of cross section of the wire is 1 mm square. Now, we this length is extension is given in mm. So let us convert all the quantities into millimeter. So this is 1 meter and it is equal to 10 raised to power 3 mm. Okay, so area is equal to 1 mm, square is given in mm square, and we have to find out the Young's modulus. Now we know that the weight of the wire, this is weight, and weight applied on the wire upon area is stress, and stress is equal to delta L by L into gamma. So if we see that W is equal to gamma A by L into delta L. So the graph between W and delta L has a slope of gamma A by L. So slope of this graph is gamma A by L. Now gamma, you can see that the slope of this graph is y upon x. This y is 80, 100 minus 20, and this x is 4. So the slope is equal to 80 by 4, which is equal to 20. So this is 20. Now we can see that gamma is gamma, and A, area is 1, and length is 10 raised to power 3. So gamma is equal to 2 into 10 raised to power 4 Newton per meter square. So this is the Young's modulus of the wire. Now we move on the next question. In this question, we have to find out the interatomic force constant for steel, and it is given that Young's modulus of steel is 2 into 10 raised to power 11, and the interatomic distance for steel is 3.2 angstroms, which is 10 raised to power minus 10. So we know that the interatomic force constant K, so this is interatomic force constant, it is equal to gamma into R naught, where R naught is interatomic distance and gamma is Young's modulus. So K is equal to 2 into 10 raised to power 11 into 3.2 into 10 raised to power minus 10. So this is 64. K is 64. Okay, and the unit of this K is Newton per meter. Okay, so this is the interatomic force constant. Now we move on the next question. In this question, it is given that for a given material, the Young's modulus is 2.4 times that of the rigidity modulus. So we have to find out the Poisson's ratio. So we can say that the formula which relates Young's modulus with rigidity modulus is gamma is equal to 2 neta 1 plus sigma. So gamma is 2.4 times of rigidity modulus, and this is 2 neta 1 plus sigma. So cancelling this out, this is 1.2 and it is equal to 1 plus sigma, and sigma is equal to 0.2. So this is the value of Poisson's ratio. Now we move on the next question. In this question, there is a steel wire which is suspended vertically from a rigid support on the roof, and it is loaded in air with a weight of with some weight, and due to that weight it expands by a length of LA in air. When that weight is completely immersed in water, then extension is reduced to LW. Then we have to find out the relative density of the material of the weight. So when that weight was in air, the load was mg, and this mg is the force with which we are expanding that wire. So it is proportional to, mg is proportional to the extension in the wire, which is equal to LW. This is derived by stress strain proportionality. In fact, this is LA in air. Okay, so let us assume that there is some constant C. Now that weight is completely immersed in water, then the net extension will be mg minus buoyancy. That will be C into LW. Now if we replace this mg by CLA minus buoyancy is equal to CLW. So buoyancy will be equal to CLA minus LW. Now the relative density is equal to the density of that solid upon density of water. And it is also equal to buoyancy, in fact mg upon buoyancy. Okay, so mg upon buoyancy is relative density and it is equal to LA upon LA minus LW. So the correct option will be option number A. Now we move on the next question. In this question, it is given that there is a bar of cross section A and this bar is pulled by a tensile force from both directions F. So net force would be 0 and this bar will not move. Now there is a cross section here which is at an angle of theta with this line, and we have to find out the stress developed on this cross section. So first of all, let us say that the area of this cross section is A dash. Let us assume. So A dash cos theta is equal to A. And therefore, we can say that A dash is equal to A upon cos theta. Now we know that at this cross section also, if I draw the diagram like that, we know that this force F and F is keeping this small bar at rest, and therefore the component of this force along this direction will be F cos theta, because this angle is also theta. So stress, we can say that stress would be perpendicular force F cos theta per unit area. This is area will be A dash. So this stress is equal to F cos theta upon A dash, where A dash is A by cos theta. So this stress is equal to F cos square theta by A. We can also say that this is a longitudinal stress or tensile stress. But if we wish to find out the shear stress, then we can say the component of F along this line will be F sin theta, and shear stress will be equal to F sin theta upon the area, which is A dash. So it is F sin theta cos theta by A. So this is also F sin 2 theta by A, 2A. So in this question, tensile stress is being asked, and therefore the correct answer is F cos square theta by A. And for shear stress, the correct answer would be B.